So, some background on the gas turbine is they operate off of a Brayton cycle. They're mostly used in aerospace as well as power generation, as you can see with the big turboprop or the supermassive one in a power plant. The general process, which I believe is next, is laid out here. So you have from 1 to 2, the air goes through the compressor, which increases the air temperature, which then feeds into the combustor where the air is mixed with fuel, and then the expansion where the exhaust leaves the jet and then goes through the free turbine, which then spins the generator to generate electric power. And here's a cycle diagram.
So the goal of the experiment was to understand the operation of a gas turbine cycle and to collect and analyze the data from the compressor turbine and generator performance. And we also applied the first law to get some steady state flow information. So for the procedure, we had to check the fuel, air, and our oil pressure. That was a mess. And then we had to do a bunch of safety stuff and connect the DAT to start the turbogen software. And then we increased the throttle to operating RPM and recorded the pressure, temperature, RPM, voltage, current, and fuel flow, as well as the power. And we put it into Excel for analysis, and then shut down the experiment. So our data acquisition, we had pressure sensors and temperature sensors at the inlet and outlet of the compressor and both of the turbines. We also measured the generator RPM and the engine RPM, and then the fuel flow and the power output once the load was applied. So the data that we obtained, again, is the compressor, inlet and outlet temperature and pressure, as well as the inlet and outlet temperature and pressure for both of the turbines. We measured the fuel flow of kerosene, the engine RPM, the generator RPM, and the voltage, current, and power of the generator. So here's where our data starts. As you can see, there's a huge negative spike in pressure. That correlated with a spike in the fuel flow. So it's probably some like fuel dump that like didn't burn properly and caused back pressure that messed with the sensors. You can go to the next one. You can see that also with the temperature, there was a huge temperature spike, and that's going to be a kind of consistent thing across these. They're just going to have random jumps in temperature and pressure in either the positive or negative direction, mostly at the same point that the fuel flow peaked, so it's probably all a related issue. See that again. That's the huge, I doubt it measured negative 37,000 Celsius, so it's just a sensor issue. Again, negative 60,000, that's even colder. So see, that's the jump in the fuel flow that I was talking about. So that was probably just a random like measurement issue. And then there's once we started to like apply the throttle and the fuel was going through. And then that's the engine RPM, generator RPM, generator voltage, generator current, and generator power. So, the uncertainties, the potential sources of error come in delay in data acquisition sampling, incomplete combustion, which is what I said could have possibly caused that like fuel and temperature pressure error, sensor error or misreading gauges, another reason for the spikes, and setup is not properly designed or damaged. Richard told us a lot of things about that. He wasn't happy with the amount that the school spent for pretty not worth it equipment, so it could have just been the machine.
So here's the steady state analysis that we did. I took readings from our data at the max engine RPM, which was just about halfway through the experiment. So here is the inlet and outlet temperatures for the compressor, power turbine, as well as the free turbine. And at all these temperatures, I went and found the H values in our tables. So with those enthalpies, we could calculate different properties. So The compressor work, which I left in kilojoules per kilogram, was about 72. Heat added was about 630 kilojoules per kilogram. Then you have your power turbine work. And you can use all of this to calculate your network and then your thermal efficiency, which came out to about a whopping 3%. And much like it was discussed a couple weeks ago, this makes sense because of how small scale our model was, and how much.
So again, the efficiency was only 3.13%. Typical turbojets have efficiencies in the range of 30 to 50%, and that's because they're much more well designed. You know, they have millions of dollars in research and development as well as like manufacturing costs. This one probably had like faulty like connections, whatever, that allowed for air leaks and stuff or things like that. So I mean, it's probably not the most well-designed machine, and that is part of the reason why the efficiency is so low. There's also a non-ideal irreversible compression in the compressor, and then there's compressor and friction in the turbine and compressor. Incomplete combustion could also contribute to these losses, and there's non-ideal turbine expansion, work extraction. There's a bunch of things that just lower that efficiency since they're not optimized for this setup.